how they integrated ChemAxon's naming technology and how they can use their text mining tool to extract chemical structures and properties from tables. He also is going to do a little demonstration. And in the end, we're going to have a Q&A session to answer your question. So this slide shows how we integrate ChemAxon's technology with Linguamatics text mining tools. As you can see, ChemAxon is actually used in multiple places. So first, we have the structure query tool Marvin that is now available from I2E. You can also do substructure and similarity search using our JChem technology. And also, because Linguamatics has a lot of patents and other documents, naming tool is used here to extract chemical information from these texts. This will be the focus of today's talk. And also, USPTO published a lot of the US patent, including MO file for the structures, and ChemAxon's JChem technology is also used to convert these MO file to structures. So today, I'd like to focus on our naming technology. Naming is a broad term. It actually includes multiple products. First, we have structure to name that can convert a chemical structure to different chemical information, including a preferred IUPAC name, or it can convert to a traditional name, or even a CAS number. And this tool has reached its maturity. We can also do the reverse, which is to convert different type of chemical names to structure, including, for example, IUPAC name, CAS name, other systematic name. We also have a large dictionary of common names. We also support CAS number to names, CAS number to structure conversion. We also can convert fragments, for example, homology groups in a patent claim like R2 group, methyl group, etc. And we're going to include biological names too. We didn't stop there. We actually extend the naming technology to other products that can extract chemical information from documents. For example, document to structure. If you have document to database, if you have a library of documents, these could be put in a repository system, and we use naming technology to convert them to a structured database. And also document annotation that can generate HTML file and provide you an interactive visualization of the structures. I'm going to give a little demo in today's webinar. So I think the main topic here is name to structure conversion. Like I mentioned, it's already a mature technology, but we're still constantly making improvements. For example, in the latest version, you are able to convert these complex names. For example, this one has multiple spiral ring center. We can convert this complex name to structure. We expand this technology to how to extract chemical information from patents. So let's say you have this chemical patent, and naming will be able to identify a chemical entity in the document and convert this chemical name to a structure. Not only we just give you the structure, we also tell you where this structure is located. For example, this structure is on page 28, and we also give you the context, like example 1 before this name. So it's very easy to go back and look for this information in the document. Like I mentioned, we expand this technology, for example, in document annotation. So if you have a patent XML, I'm actually going to switch to my demo. So this is a patent XML published by USPTO. We're able to generate a HTML file that's formatted and with all the chemical information highlighted. Now, for example, if I want to look for example 1, I can just do a text search on the page. Here is example 1, and the chemical name is highlighted. And if you move your mouse next to it, the structure will be displayed next to the name. So this is a very interactive way to display the chemical information. Of course, a lot of the patent text are from OCR, and there can be all types of errors that OCR can make. We do have a correction algorithm in our naming technology that looks for the common mistakes that OCR may make. For example, in this case, the M in methyl is RNN, YL is Y1, and oxygen here is 0. These are the common mistakes, and the correction algorithm will identify these mistakes and correct them before we make the structure conversion. So we actually had a collaboration with Linguamatics on a project called CHICO, Chemically Informed Knowledge Extraction from Literature. This is a 2-year project supported by the EU Eurostar program, because Linguamatics has a lot of patent documents, and we applied our naming technology on this document to extract the structures out and also compare with the manually indexed data. And as you can see, our product has been improving during time, and the overall score, F score, which is based on both the precision and recall. Recall means how much relevant information we can extract. And precision means out of this extracted information, how many structures are accurate. And the overall F score is 90%, which is pretty good. And this is actually before version 6.0, and now we're on version 6.1. In fact, by the end of the year, it's going to be 6.2, and the F score is going to be even better. Of course, there are some names in the patent that we cannot convert. And in most cases, I wouldn't say in all cases, but in most cases, there's actually something wrong in the name. So for example, this is a name from a patent document, and there is no OCR error. It looks like a legitimate name, but naming cannot convert to a structure because this name is actually wrong. It has 4-methylsulfonyl. There's no 4-methylsulfonyl. The correct name is probably this, and then our naming can convert it to a structure. So this slide, just want everyone to keep in mind that a lot of people think that the patent should be very accurate. There's no mistakes. But actually, I've seen plenty of cases. A lot of names can be ambiguous, and there are different levels of ambiguity. So far, I have to talk about our naming technology, which is all based on the English language. And now I'd like to talk about the new edition of our naming suite, the Chinese name to structure. Here's a little background information. This graph shows the top 5 patent offices in the world and how many patent applications they have received. As you can see, by the year 2002, Japan is #1 patent filer in the world. US is #2, and Korea, Europe, and China are 3rd, 4th, and 5th place. 5 years later, US has surpassed Japan to become the top filer, and China jumped to #3. And then last year, China has surpassed US and become the top 1 filer in the world. Now Japan is #3. I want to make one note that the reason that Japan Patent Office is not number 3. It's not because Japanese scientists have become less innovative. It's because the Japanese Patent Office passed a new policy. Because before, a company can publish multiple small patents on the same invention, but now they have to file one big patent. So the number of patents may decrease, but the number of structures for the chemical space is still growing. So because now China is #1 patent filer, it'll be very important to be able to mine the scientific literature in Chinese language. So as I was showing before, with name to structure, you're able to convert all kind of chemical names, trade names, or cast number to structure. And now we also added a new member to this family, Chinese name to structure. The mechanism of Chinese name to structure is actually very simple because we already have a very mature English name to structure conversion. So what we need to do is to find equivalent for each entities in the Chinese name and convert to English. So for example, this is the IUPAC name, the Chinese IUPAC name of aspirin. And we simply need to have a dictionary and look for the English equivalent. So if I see Yixian, then that's acetal, Yangji, oxy, benjasun, benzoic acid. And we put everything together, and we can convert this to the structure of aspirin. Of course, Chinese and English are two different languages, and so are the chemical names. So there are a lot of challenges. Here are some examples. For all the ester and salt, the order of these names are actually different. So for acid, acetate, the structures has the acid part and the alcohol part. And in Chinese, you actually said the acid part first and then the alcohol. But the English name is, the order is reversed. Here's another challenge. The English names sometimes also have alterations. So for butane, the buta is the prefix for 4 carbons, and ane is for alkane. But when you put them together, you actually remove one of the a's because you don't want double vowel. And the other challenge is for Chinese, there are a lot of characters, but the same characters can have different meaning in different contexts. So for example, this character means salt, and this one means acid. But if you put them together, it means hydrochloric acid. So we did make a lot of improvement to our naming technology to accommodate all these challenges. The trick here is not to make the translation perfect, but to make our naming more tolerant to different mistakes. We'll be able to overlook these mistakes or challenges and still generate the correct structure. So we did do validations on these, our new Chinese name to structure. The first test we have, we collected about almost 40,000 Chinese names and their cast number. This test set is collected from the internet, and as you know that a lot of information on the internet is not correct, and so is this test set. So it does have some unusual, incorrect, ambiguous names. And the conversion rate depends on how you want to count it. If you convert the English name to structure, if you only do the Chinese name to structure conversion, the rate is about 69%. But if you consider the structure can be converted from the English name, it's about 79%. The overall accuracy is about 91%. The second validation we have is on Chinese patent. So we are provided with 54,000 Chinese patents document from an unnamed source. And not only have the Chinese text, we also have the machine translated English text. These translations was not done by us. So first we did a filtering. We want to look at patterns with at least 20 structures, and these structures have at least 20 heavy atoms. So sodium chloride is not considered a structure. After the filtering, we have about 2,000 patterns remaining. And because we have to do, this is patterns, so a lot of them are from OCR, then we have to consider the OCR error. Take this example. This Chinese name means 3-phenylpropanic acid. So let's say I don't speak Chinese. I want to know what the English equivalent is. Let's just use, for example, some freely available translation tool like Google Translate. If I just copy this text into Google Translate and click Translate, this is the result I'm going to get. Instead of 3-phenyl, it gives me 3-butyl-propanic acid. And the reason I get this result is because the text I use is actually after a Chinese OCR, and it's actually not the same text, but actually only one character is different, and only one small part of this character is different. But this character means phenyl, and the other character means stupid. So as you can see, if you do not use Chinese OCR, then you may get a very interesting result. So like mentioned, we have a correction algorithm to automatically identify OCR mistakes, and we also apply to Chinese OCR errors. Back to the 2000 patent, Chinese patent test set. So in average, we can extract about 50 structures per patent. And out of these 50 structures, 35 are unique structures are from Chinese name only. And about less than 15 structures are from the English name only. Only about 1.2 structure per patent are from both Chinese and English names, which means there could be a lot of corrections. There could be, the English translation could be wrong in this case. And also, out of these 35 Chinese structures, about half of them, 47%, we found Chinese OCR errors, and we have to use our correction algorithm to convert them. Here's some additional challenge. Because when we're provided with a patent text, one difference in Chinese languages, there's no space between characters. So if for a Chinese speaker to be able to identify where the chemical name begins and ends, and also is our naming technology. We'll be able to take a Chinese text, identify the chemical entity from this text. And in addition to this challenge, the XML files, there's also a lot of markups, like different tags. We're still able to overlook these challenges and convert to the structure. So, for example, this is a Chinese patent XML. It looks actually like this. There's a lot of text. There's also line break in the middle of a name. We're able to, again, generate an annotated HTML. And if you move your mouse next to the structure, you will see this. If you move your mouse next to the name, you'll be able to see the structure. So I think that's all I want to talk today. As you can see, Chinese patent is now #1 in the world, so it's very important to mine this data source for IP protection. But the machine, if the machine translation algorithm for general purpose is not enough, and also if the translation doesn't do OCR, it doesn't consider OCR error, it's going to give very inaccurate result. With our naming technology, it provides a fast and reliable conversion. It can also extract information from patents. And as you can see, our Chinese name to structure already gives pretty good result. And the advantage is our naming is very flexible. Not only you can use it in all our tools, we provide the API, so it's very easy to integrate with our collaborators. For example, our Linguamatics I2E system, which you will see in a little bit. So I think that's all for today. I talk about our naming technology in Chinese and English. But if you're wondering what we're working right now, I can show a little demo video. This is Marvin's Sketch, which is our sketching tool. If I want to import a name, I can copy this name and paste into the text box. Click import, and it will convert to the structure. And this name is not Chinese. It looks like Chinese. It does have some Chinese character, but it's actually not. You probably guessed. It is a Japanese name. So right now we're working on Japanese name to structure conversion. In fact, I've been doing some validation of our development. So far, our precision, the accuracy is about 98%. So it's pretty good. So I think I will stop now, and I will switch to Dr. Millward, and he's going to talk about I2E, how they integrated our naming technology. And if you have any questions, we're going to have a Q&A session at the end, and I'll be happy to answer your questions. Thank you.
Thanks, David. Okay, so I'm going to say a little bit about Linguamatics I2E chemical text mining. I'll just give a very brief overview of the I2E system more generally, and then go into some of the details of the integration, and then talk about some of the latest work on table processing. So the I2E system is an agile text mining system, and that's slightly different from traditional natural language processing. So traditional natural language processing involves programming in your different queries or machine learning from relevant annotated data. Agile NLP, in contrast, gives you an experience a little bit more like search. So you can iterate, develop your queries, and you take a data-driven approach to exploit unannotated data. So you generalize queries, see what's in the data set, and then develop your queries from that. But you're still getting the precise structured results of traditional NLP and all the power of NLP behind the system. So it's combining the natural language processing, the search, and the concept identification, which can be from various terminologies and dictionaries, or can be from ChemAxon's naming technology. So this gives you a variety of strategies to find information. It can give you can use terminologies, and if you're searching for something like cancer, it's not just giving you the synonyms for cancer itself, such as malignant neoplasm, but also giving you all the children, such as leukemia or lymphoma. So that means that one search term, one search concept, can actually search for thousands of different terms, or even tens of thousands. There's the natural language processing, which allows you to split the text up into meaningful units, and gives you the possibility of very precise negations, for example. So you can look for things like pressure, but not blood pressure. You also have regular expressions, so you can look for microRNA syntax, and the users can do this on the fly. They can create their own regular expressions within the query patterns. Chemical substructure and similarity search, which we'll say more about. But then there's also the aspect that you can do things in a high throughput fashion. So you can put in, for example, a list of 500 genes from a microarray experiment and say, what properties do they have? Is there any information in the literature already about those particular genes and relationships to diseases? So that high throughput aspect is an important part of using text mining. And it means it's also you can use text mining in automated workflows, for example, with Pipeline Pilot and 9. So we're going from the surface form of a word to the semantics. So in this particular sentence, we've got a compound here. We can find out its structure using the name structure. We can find in this case we've got COX2. We can also look that up in our terminologies and find an entree gene ID for it. And then we have the word inhibitor, which we can find as a relationship. And then we can use the sentence structure to say that actually it's the compound inhibiting the gene. So different ways of expressing things, whether different words to express the same concept, different grammatical structures to express different relationships, we can standardize all that and get one representation out. And once we standardize things, that allows us to then cluster results more. We can send the results to semantic stores. We can do slice and dice the results in different ways. So we can focus on the facts that we're extracting from the documents as opposed to focusing on the documents themselves. And it means we don't have to read as much or we read in a different, we prioritize our reading in a different way. So looking at some of the chemical information, we can access chemical information from lots of different data sources. It can be proprietary documents, such as internal study reports. It can be external documents, such as patents, journal articles in PDF or XML, and things like the FDA or EMA drug labels or approval documents. You can run I2E on, as an enterprise server, or you can use I2E on demand, which is a hosted version of I2E, which we supply. And we've actually found quite a lot of customers are now using a combination of both. So they have I2E Enterprise for their proprietary documents, but then they use I2E on demand for common data sources or patents, such as patents or Medline, for example. And you can automate via the Web Services API. So that's a very rich web services to access, ask the system to index documents, make queries, for example. And then there are components, the Pipeline Pilot and KNIME, which access I2E through its Web Service API. And in I2E 4.1, which is the current version of the software, you can access the internal content and the external content seamlessly through the same interface. So a single user can actually access proprietary documents on their internal enterprise server, but also just as easily access information from Medline or patents on the on-demand hosted server, all through the same interface. So it makes it relatively seamless whether the data is stored on an internal server or an external one. And just a couple of words on the patent solution. So the patent solution at the moment has over 20 million full-text documents from USPTO, EPO, and WIPO, so applications and grants, and that's from the IFI Claims Direct asset. So you can do interactive querying over that full set of 20 million documents. Okay, so now a few words about the integration. So David went through the general structure and the components. I'll now go into a little bit more detail into each of these. So first of all, the naming, we use the ChemAxon's name to structure, and we create the chemical concepts on the fly as we process the documents. And you can choose to identify the concepts either according to SMILES or according to INCHI. So when you build an index, you can make the choice of having identifiers of SMILES or INCHI. And then we also use structure to name to give a standardized name for the structure we found. So that means that you may have, in some cases, you may have a structure in the document, an IUPAC name in the document. Sometimes you may have a dictionary name. We provide the same standardized names, so they'll be clustered together. There's then substructure and similarity searching, and you can use Marvin's sketch to draw the chemicals. There's substructure similarity searching, and also in I2E 4.1, you can save the searches and then run those against different sets of documents. So 4.1 actually integrates the substructure and similarity searching much more deeply into the product than previous versions of I2E. And that means that you've now got scalable substructure and similarity searching across millions of documents. So to give some examples, here's some examples of our UPAC names in the document, and then we've standardized and used name structure to name to give our own preferred naming for each of the compounds. And in this case, we've just done a substructure search for this particular compound. In this next example, we're looking not only for the compounds and then we'll pull out their structure, but we're also looking for melting points or boiling points within an appropriate context. So we're looking for the melting point appropriate, for example, 31, as opposed to, for example, 32, for example, which might follow directly afterwards. So we're allowing appropriate context between the melting point and the compound. So this is the first example of where we're using both the chemical substructure search to actually find particular chemicals of interest, but then we're combining that with linguistic search to find other information in the document, such as a melting point. We can output to JChem to Excel and then use JChem for Excel to actually show the images of the chemical compounds, and actually you can click through and actually open those up in an editor. And so you can present the results, export to Excel, and then slice and dice them within Excel. And if we want to, when we're looking in patent documents, you can get thousands of compounds from a single patent document. We may want to separate those out, cluster them according to different properties. So this one's an example just where we're looking at compounds which are mentioned as products of a reaction. But we can look for things like the solvents and cluster the different compounds according to the properties we find in the text. That allows us to rule out some of the information we may not be so interested in. So the particular construction here is looking for things which give or yield, and then an optional amount construction followed by the actual chemical name. So now I'll say a little bit about table processing. For table processing, at the moment, it's not yet on our hosted patent solution, but we are using it for various customers already on different document sets, and we will sort of put it onto the hosted solution at some point in the future. But we are still fine-tuning some of the table processing. So tables are pretty varied. So we pre-process tables from HTML, XML, PDF formats, either text or images, and we create a more common format of the table. We allow for things like headers or cells spanning multiple columns, and for there being multiple headers at the top of the table. So in this example here, we have the percentage reporting event is a header which crosses over two columns, and then we have the individual column headers below. This is an example from an FDA drug label, and the left-hand example is from a patent document. So when you're extracting a table, you can actually just try to extract everything and just present it in a way that will make it easier for further processing. In this particular case, we've taken a table, and then for each row, we're giving the table title, we're giving the column heading, the row heading, and then the value of the cell. So that's a kind of way of sort of pulling out a complete information for the table. A more common request, I think, is where you're looking for something more specific within tables. So in this particular case, we're looking for particular compounds, we're looking for HDL values, and we're pulling out the cell content and the units of measurement. In that case, it's a more guided search. We're saying we're particularly interested in the HDL values for compounds in these patent documents. So we're using the ontologies so that we can pull out different ways of referring to the different compounds, and then we're pulling out the numeric values and the measurements in the table. So having a look at some examples from the FDA drug labels, in this case we're looking at adverse events, and you've got an information. The original table is the one on the left. This shows some of the highlighting, showing where we've highlighted the values that we've pulled out. And on the right is an Excel spreadsheet where we put the data that we've extracted. So looking at the final result here for anorexia, we pulled out 8% for the compound and 4% for the placebo. And that's then showing up in the Excel spreadsheet with 4% for the placebo, 8% for the compound. So you're pulling it out. So this was the original text document. You're now getting it into a structured form in Excel, but it could also go directly into a database. When we're looking at things like structure-activity relationships, you find that in patents, the information is often spread across different parts of a patent document. So it's not just a matter of pulling out the information from individual tables, but you have to combine information together from different parts of the patent document. So in this case, we've got an example 10 here, and we've got the definition of example 10 here as a particular compound. And then later on in the document, it talks about potency values within a table. So we combine together the tabular information, which gives us a potency of 10 nanomolars, with the exemplified compound definition earlier on in the patent document. And this is very common with the SAR extraction. It's not just in a single table. You have to start combining things from across the patent document. So to give a couple of examples, in this example, we actually have an embedded mol file. So we process the mol file, extracted a structure for that. But then the actual inhibition value is given just by the plus sign here. And we actually have to look into the definition to see what the plus means. And we can actually see here that the plus means that it's 0.2, it's 0 to 25% inhibition at 0.3 micromolar concentration. So we then combine this information together, so we get the structure from the mol file, we get that it's an inhibition, we get that it's an inhibition on IL-1 beta, and that's from the mention of IL-1 beta at the top of the table here, in the table header. And you can see that IL-1 beta here was rather differently formatted, but we've standardized that. We've used our terminologies, and we've also used some fuzzy matching to actually match from IL-1-1 beta to IL-1B. And then we pulled out the 0 to 25% and the 0.3 micromolar. So that was an example where the information in the table was split up. This is an example where we've got the example 4 and then the compound, the exemplified compound for example 4, and then we've got a table which talks about an example number as number 4 and then gives the potency of 398. So then we can again pull together the information from the exemplified compound, get the structure out from that, and then we get the potency from the table and pull out the values from the table for the appropriate example. So again, we're pulling together different parts of the patent document, combining them together to give the final table result. So just to summarize, so chemical text mining provides access to the information trapped in the free text. It structures the information for quicker review or to feed into semantic stores. And you can extract from tabular information, and that's possible for a wide range of documents and table formats. There is a long tail of less predictable tables, and we're still working on queries to try to pick out more of a sort of tail of less standard formats. And I should say the quality from PDFs will vary. So PDFs are pretty good if you've got lines around the table. They're not so good if you haven't got lines around the table. So the PDFs will tend to be the worst quality. Okay, so I'd like to acknowledge again the Chickle project from the European Union Eureka's Eurostars program, and also Daniel Bonio from ChemAxon for the work on name structure, and Himanshu Agrawal for the table processing work. So I'll now move into a quick demonstration, and then we can go into questions. Okay, so this is a view of the I2E Pro interface, and I've got a very simple query here of just saying that I want to have a chemical and a kinase together, in this case just 10 words apart in any order. For the chemical here, I've restricted to a particular structure. So if I open up Marvin's sketch, you can see I've actually drawn this particular chemical, and this is the chemical which is then going to be used in the search. So we're taking this particular structure, and then we've decided to use this as a substructure search. We could have also done a similarity search with a particular threshold. In this case, we'll do a substructure search of this particular chemical, and we're looking for the word kinase within 10 words on either side. Now we're running it over, in this case, a small set of around 100 patent documents, so you can see it's taken very little time to get back the results. And we can look at the hits here, and we can see that one hit was a system systematic name. The other hit was allotted, which would be a dictionary name. So in one case, it's taken the dictionary item, it's looked up and the known structure it has for that dictionary item. In the other case, it's taken the systematic name and it's found a structure for that. And it's come up with the same structure in both cases in this case. And we've clustered them together with its preferred name, which in this case is allotted. It uses the preferred name from its dictionaries if it has a dictionary definition. Let's just actually have a look in the patent document itself. So we can see the actual hit in the document. This is giving the different, we have gefitinib and allottinib, they both hit with this particular substructure, and then we have the systematic name as well. If we go to the top of the document, you can see the actual structure of the patent document. That's a very simple search. Let's have a look at the melting point and boiling point example, and then we'll go on to some table examples. So in this case, we're going to look for any chemical, and we're going to look for melting points and boiling points. So in this case, we're looking in this particular document. Let's click through to one of the examples. So you can see here we have the example 58 and the melting point here. And the system has actually tied together the correct melting points with the correct examples. So for example, the example 56, it's tied it together with 148 to 149, and example 57 with 52 to 54. And it's not got the wrong melting points with the wrong compounds. So you're using some contextual information here to make sure that you tie things together properly. So now let's move to some table processing examples. So I'm looking in one, I'm showing an example of one particular patent here, and I'm using this particular patent because it has tables of different formats within the same patent. So in this case, we've got the values here of a particular chemical we're finding in inhibition, in this case, of IL-1 beta at greater than 76% at 0.3 micromolar. So let's have a look at this second example first, and then I'll move on to the first example. So we can click through to the documents, and then we find the information in the document, and we can see that in front of the table we have the definitions of the particular pluses and stars. The reason the final one isn't highlighted is that actually none of the compounds actually had an inhibition with the 4 stars level. And then below you can see the different mol files, and in the column here we've got the IL-1 beta percentages, and you can see you've got the different pluses values, and those are the ones we're going to connect together and get the appropriate inhibition value. So that's filling in the first example. Let's have a look at this, the example above. This is a different format. This is where you're getting IC50 values out. And the IC50 values are then you're interested in the particular concentration where you're getting the inhibition at 50%. You're interested in the nanomolar concentration here. So let's have a look at this example. So this is a rather different table. And if we look at the top, we find that this is a table with IC50 values, and in this case we're just getting the ID numbers and the concentration values. And in this case we're having to connect up the ID numbers with the particular compounds that we found in the table above. So we're connecting up the IDs here with the IDs that were specified in the table above, which was giving us the mol file and the constructions above. So we're using the mol files here connected to ID1, and then we're connecting those together with the table values below. So once we've created our outputs, we can then, for example, go into Excel, and if we want to, we can move into Excel, and then we can use JChem for Excel to show the actual images in our Excel output. Okay, so I'll finish there and see if there are any questions, both for my talk and for David.
Thank you, Yanqi and David. Yanqi, would you like me to read some of the questions?
Hey, thank you. Thank you both of you, David. Yeah, sure. I think I've shared some questions with you, David, so go ahead.
Okay. I can see some of the questions. I already answered some questions. For example, someone asked if there is an interface for implementing other name-to-structure converting software like Opsin. So right now it's not supported out of the box, but because ChemAxon's software is very flexible, so it can be done with, for example, a web service or a custom converter using API. So that's possible. Also, another question about the breakdown of the patents. I showed the plot for the top 5 patent office. That is for the total patent. I do not have the number for chemical patent, but I hope it's also proportional. Another question, I stopped typing because it may be easier to answer. One question is they have a lot of CAS number and registration numbers. Is there a way to incorporate this into our naming technology? So yes, in fact, you can have a customized dictionary that you simply have the compound number and the structure. So it's like a pair. And you just put that, could be on your local computer, or you can use a web service. And whenever we see this compound number in a document or on the fly, we can just look it up in the dictionary and convert to a structure. So yes. The other question, I'll read it. So for Chinese language patents, what is the source of the text? And also with my previous question about English language patent, how is the chemical names recognized and extracted for translation? I think there may be some confusion. Apologize if I didn't present it clearly. But for the second Chinese name-to-structure validation set, so a name source provided us with Chinese patent XML. These XMLs are OCRs. So the OCR, the patent text, convert them to XML and provide it to us. This is Chinese patent text, and also they use machine translation method and translate to English XML. And we simply run our Chinese name to structure on the Chinese XML and our regular naming on the English XML, and then we combine the result together. And that's how it is shown. Let's read another question. Your IUPAC name from structure to name certified by IUPAC. We are not aware of there's such certification, but we did follow the IUPAC naming, the preferred IUPAC naming convention very strictly. And if you can provide us with more information on the certification, we'll be happy to do that. Next question, where does the patent text you use come from? You mentioned USPTO XML, but you also mentioned OCR and its mistakes. Are you OCR-ing the PDF? So again, we definitely use the USPTO XMLs, which is OCR'd. But with some of our tools, for example, documented structure, you can open the patent PDF. And documented structure would do OCR and then correct the mistakes and then extract the chemical information out from this from the PDF. Next question. How do you identify the chemical names in the text? Is there an algorithm for identifying extracting the chemical names? Is it a Linguamatics algorithm or a ChemAxon algorithm? So our naming technology can can identify the chemical name from the text. So if you have a document with different text in it, naming will be able to see which part is a chemical name and convert to a structure. So it is our algorithm, but I'll also let David to comment on the linguamatic algorithm.
Yes, so we call out to the ChemAxon name to structure for finding the systematic chemical names. We do some work in reducing noise for certain chemicals, and we also have ontology dictionary-based chemical recognizers, and those dictionaries also include the structures. So we sometimes use those in addition, because sometimes people want to use different identifiers from particular terminologies. So sometimes they want to be able to do the substructure similarity search but use particular identifiers. But obviously if you're using the dictionary-based methods, then you're not picking up the systematic chemical names. And the systematic chemical names tend to be really important in the patterns, possibly a little less so in things like Medline, where typically they are sort of known chemical names.
Thank you. Let me read the next question. How is the ambiguous naming correction is performed? This is actually a very complex question. I actually didn't have a lot of time to show other examples. There are different levels of ambiguity. So if it's a simple ambiguous case, then we actually import the structure, but we flag it saying this is ambiguous from an ambiguous name. But sometimes ambiguity is too much, then we cannot import them because you need some menu invention to correct the name. And we do use the algorithm to convert that. Sorry, David, go ahead.
Yes, so I have a question here on about optical structure recognition, and so yes, we are looking at optical structure recognition, and do you want to actually say a little bit about ChemAxon's integration with optical structure recognition, David?
Oh, like David mentioned, we can also our document structure actually can integrate with other optical recognition software like Clyde, Astra, Imago. As long as you have the software on your computer, using our document structure will automatically call this software. If we see there's an image in the document, then we'll convert that to structure. Also tell you the location of that structure.
And a follow-up question was looking at Marcouche and R groups, and yes, that is something where we have got some work going on, looking at some of the linguistic constructions involved in the R group definitions. But that's relatively early work at the moment.
Let me read another question. How do we access ChemAxon APIs? Actually, very easy. When you license the software from us, for example, if you want to license naming, you can use it in different formats. You can use it from the GUI, from command line. We also provide the API, so it's the same. It's available in different formats, and if you want to evaluate, we can certainly give you a trial license to evaluate. Let me read another question. How much unique medicinal chemistry are you finding in Chinese patents? And don't Japanese companies file US and PCT as well? Actually, I cannot comment on how much unique chemistry can be found in Chinese patents, because that really requires the extensive research on this topic. also not sure about the Japanese company's finding policy.
Okay, so I have a question about limiting searches. Oh, sorry.
Sorry. The important aspect is, even though they filed the patent in the U.S. And PCT as well, it is important that where they filed it first, there could be a lag for the other locations. For example, sometimes there's usually a 6 months lag. Go ahead, David.
Yes, so I had a question. Is it possible to limit searches to only those compounds with desired data and ignore structures without data? Yes, and that's certainly the case. And you can make it. You can do either. So the examples I showed were ones where the compounds were linked to structure activity relationship data. But you can also make those linkages optional so that you show the compounds whether or not they have that information. But often, yes, you want to sort of restrict to the compounds which do have the information about them.
Next question. Can you describe how you calculate the F-score for English and Chinese entity recognition? The F-score is a combination of precision and recall. And the algorithm is actually the standard algorithm. I actually asked this question to Daniel before, and he actually sent me a link from Wikipedia on F-score. But it's actually a pretty standard way to calculate that score.
Okay, I have a question which is saying, what do you do about things where it might be chemistry, but in some cases the conversion might have failed? And so yes, we can do that, and actually that was how we did a lot of the evaluation in the Chickle project. We actually used linguistic patterns to pull out likely chemicals with systematic names, and that allowed us to then pull out tens of thousands of names, and then we could see what recall we were getting with the name structure. So that can be a useful way of testing the system, but you can also use it in your queries as well. So you can use the linguistic patterns and use linguistic constructs to sort of pull out likely chemical entities, and then you can add those on to the ones you're finding and have actually given a proper structure to.
Next question. Is the Chinese name-to-structure function included in the current version of Marvin's sketch? It is available, I believe, since 6.0, and we're now on 6.1, and 6.2 is coming out by the end of the year. So yes, it is included in the current version, but you do need a license, additional Chinese name-to-structure license to unlock this feature, Marvin sketch. Next question. Do you extract and enumerate McCool structures from patents? Yes, I do get this question a lot. But of course, McCool structure can be very complex. There's different complexities, like how do you extract the core, the different nested R groups. So right now, we are not able to extract McCool structures. However, we are working on how we can not completely do this automatically, but how we can use our technology to help you extract McCool structure. This is an ongoing project. Next question. Are there different optimized version modules for the chemical name recognition and or name-to-structure conversion depending on the used document type? Our naming technology, actually, they do handle different document type differently, but the naming part, the name-to-structure part, is the same. It just depends on how what the document is, how we process it, but the naming part is the same.
Yeah, all right.
Okay.
I think
I answered all my questions.
Yeah, I think so too. David Milford, I think you should have a couple of questions in front of you, I think.
Yes, so there are questions here about how do you measure precision and recall. So typically what we do for precision is we just use a sample of documents and then check the accuracy based on that sample. For recall, that's always more challenging because you've got the issue of have you found the particular information. The approach we tend to do for that, so for example with the table processing, what we do is we create queries which just look for tables which mention, say, inhibition. And that gives us an idea of the tables that are available in the pattern set. And then we can look further and see, are we then actually picking up the values within those tables? So what we do is we sort of do slightly more general queries to see what tables are available in the pattern documents, and then we can evaluate against it. And that means that we don't have to sort of look through every document one at a time. We can actually use the patterns themselves to give us an idea of then how well we're doing with our more precise patterns. We've got a question about when we'll see pubchem links in a column added to the results. That's something I'd have to look at. I think, yes, I think we need to add in some extra attributes to allow that. The other possibility is in I2E you can do you can add information from existing tables to your results. So if you have a mapping from the smiles to pubchem, then you could add those into your results. But I'll think about that a bit more.
I think I have another question. It's probably to the both of us. Can ChemAxon or Linguamatics be integrated in Apache UIMA? Right now, for ChemAxon, it's not supported out of the box or at the moment. But again, it can be done.
Yes. So for Linguamatics, we can take the results of UIMA named entity extractors, and then we can put those into I2E. So I2E can accept XML marked up documents. So if you've got particular annotators that you like it from UIMA, then you can use those, annotate the documents beforehand, and then I2E can pick up those annotations, and then it will create the appropriate classes, and then you can do further interactive querying over that data once it's annotated. So you can merge those in with the other annotation capabilities of I2E if you want to.
Yeah, correct. And I think that David Milford, you should have a question like about pairing up the information in different tables.
Yes. Yes. So I think, let me just, so yes, so that's probably, so you can pair the information up by the, in this case, either by the IDs of the exemplified compounds, or you pair up according to things like the plus symbols, where people are using that to denote different ranges of IC50 concentration. So for people, for I2E users, I can send some queries which sort of show how to do that.
Yeah, great. We just got another question for you, David. Can you use your table extraction on MatCam journal papers?
Yes. So we've used it on journal papers. We've used it on PDF documents, and some of the examples especially for things like the state adverse event reports, we've been using PDF journal documents for those.
Correct. I'm just, checking out the list of the questions, but I have a couple left. I'm going to just read it right now.
Okay.
David, do you have any quality metrics for your semantic information text analysis?
Yes. So we've done. We were involved in the CalBC project, which involved evaluating different systems on things like genes and diseases, chemical recognition. So we do have metrics, but you have to be a little bit careful with I2E because it does depend on the query you're using, because people will change their queries to get high recall, so when they're really keen not to miss anything, and that makes sense if you're looking for something quite rare, a rare gene, say, then you may want to have high recall of the properties you're looking for. And then people will have high precision. Typically, people will have high precision if they get a feed results directly into a database without any human curation. So it all depends on the query that you have as to kind of the balance you'll choose to your recall and precision. But yes, we have done various evaluations for the sort of I think there's an interesting paper some years ago by Johnson & Johnson where they evaluated us for protein interactions and compared against existing databases. And what was interesting there is that the lack of overlap between the curated text mine results and what was in the database. And that was partly because in the text mining you were doing it over abstracts, large numbers of abstracts. With the databases it was often over smaller numbers of full text journal articles. But you do tend to find that you get different information out from text mining.
Great. There is a question about what is the current performance measure of tabular information extraction, and could you share the sample I2E queries?
So it's still in progress at the moment. So I don't have a figure at the moment. I think we've done two separate sets of documents to make sure we're not overfitting to the first set. But I haven't got any good figures at the moment.
Mm-hmm. Yeah, right. And finally, I think that's this last one. That will the table processing capabilities of I2E be made available for all licensees of the I2E software?
So I think that's to be determined.
Mm-hmm.
So,
all right.
So please do email us if you're interested in it.
Oh, absolutely.
Yeah.
I think.
If there's any additional question, we'll be happy to follow up individually through emails.
Yeah, absolutely.
Yes, and likewise.
That's exactly what I wanted to add. I think we are running quite late, but it was definitely an invaluable presentation. I've got a couple of feedbacks in the meantime from the audience. I think with that being said, if you have any additional questions, please don't hesitate to contact us, either David Mailboard at Linguamatics or David Dang at ChemAxon, or your account manager, whoever you know at these companies. I'd like to thank you very much for your attendance, and I wish all of you a very Merry Christmas. Thank you very much. Right.
Thank you, Yachi. Thank you, David. And thanks to everyone for listening.